Thank you very much for having me. I'm going to talk to you today about some work that we've been doing across Google Research on a variety of different kinds of machine learning problems, essentially trying to build the underpinnings that allow us to build really intelligent computer systems. So one of the things that's happening today is we're running into the wall of general purpose computer performance is not increasing as fast as it used to. If you look at this graph, that's a logarithmic scale on the y-axis, and you can see a factor of 10,000 increase in computing performance from 1970 till about 2008. And then from 2008 onwards, we've only had about a factor of 8 or 10 performance increase. And so really, single-thread CPU performance has really plateaued, although the number of transistors is going up. And this is happening at an unfortunate time because we now have these capabilities and large data sets where we want to use very large, powerful machine learning models that are very computationally intensive. And we have terabyte or petabyte size training data sets that we can actually effectively use these kinds of techniques on. And then we've been developing techniques like AutoML that I'll talk about in a minute that can actually make things even more computationally intensive as we use these kinds of approaches, use computation to automatically solve problems. Similarly, as we try to deploy these systems at scale, we often have very, very expensive models, and we want to serve them in systems that have hundreds of thousands of requests per second, have to have very low latency requirements of tens or hundreds of milliseconds, and have billions of users. So that's sort of where we are today. And I'm going to do two things in this talk. One is I'm going to give a tour of a bunch of research that we've been doing, and I'm going to do it through the lens of these grand challenge problems. So in 2008, the US National Academy of Engineering commissioned a group of people to come together and think about what are the grand challenges that we should really be thinking about as a society for the 21st century. And they came up with this nice list of 14 problems. And I'm going to be talking about how machine learning is going to apply to the ones in red. I think it's actually going to apply to all of them, but in the talk, I'll only focus on the ones in red. And really, being able to apply machine learning to some of the core challenges in these different areas is pretty important. And if we were able to solve these, I think our world would be a better place. So just to go through a few of them, one of them is restore and improve urban infrastructure. And it's pretty clear that we're on the cusp of releasing self-driving cars to the public. That's going to really be transformative in terms of how we think about building cities, how cities operate. Parking lots will not really be a thing. But it's a pretty challenging problem. And it really relies heavily at its core on machine learning to really understand from raw perceptual inputs, things like camera sensors, LiDAR, radar, other kinds of things, taking those raw sensor inputs and then being able to build a model of the world around you. And then from that, figuring out what are reasonable actions to take in this world to remain safe and to accomplish the goals that you want. Get the passenger from A to B, follow all the traffic laws, and all those kinds of things. And so really, the fact that computer vision is advancing tremendously in the past 5 or 6 years really is key to making these things on the cusp of deployable. Another one that I'm particularly excited about is advancing health informatics. I'll give you a couple of examples. So medical imaging, because computer vision now works, there are lots and lots of medical imaging problems that are now amenable to automated systems to help with diagnosis. So if we look at this problem, this is the retinal image. And one of the things that ophthalmologists try to do when they look at these retinal images is to see if there are signs of a disease called diabetic retinopathy. And this is a disease that is often a complication, side effect of diabetes. And there's about 400 million people at risk for this around the world. And it's really important that those people get screened every year. Because if you don't catch this disease in time, you can actually go blind and suffer vision loss. But if you do catch it in time, it's entirely treatable. And in many parts of the world, there just aren't enough ophthalmologists to do the scanning and interpretation of these retinal images. And the grading scale is 1, 2, 3, 4, or 5. So we've been doing work on this problem for quite a while in our group. And we've published work at the end of 2016 that showed that we now had a model that could take these retinal images and produce predictions that was on par, slightly better than board-certified ophthalmologists in this task of grading for diabetic retinopathy. And that's pretty good, because that by itself is useful. But since then, we've been working on improving the quality of that system. And we're now on par with not just board-certified ophthalmologists, but actually retinal specialists, which is a higher standard of care. And so that's pretty important. The way we sort of made that improvement is we changed the way that we labeled our training data. So instead of having independent evaluations by ophthalmologists, we had a group of retinal specialists come together for each of the training images and make a consensus decision about whether this should be a 2 or a 3. And that allows us to get higher quality training data and to get a higher quality model as a result. So that's pretty exciting. The other thing that's kind of exciting, though, is we can make completely new kinds of discoveries from this data that doctors didn't really know that these signals existed in these kinds of images. And so I'll tell you kind of a funny story. We had a new person join the diabetic retinopathy team in our group. And to help get them familiar with the software stack that we were using, one of the people involved, the head PM, Lily Peng, said, hey, why don't you go off and take these images and see if you can predict age and gender from the images? Because we had some data that had both the retinal images and some clinical labels like that. And they thought that age would be predictable only within a few decades, and the gender wouldn't really be predictable, so the AUC would be 0.5. And so this person went off and ran the code end to end, and came back and said, hey, I can predict gender with an AUC of 0.7. And people didn't really realize that there were signals of gender in these retinal images. And so Lily said, oh, no, that can't be right. Go check your work and come back. And so the person went off and came back a few days later and said, hey, my AUC is 0.85. And so that started an investigation into what other things could we predict from these retinal images. And turns out there's a bunch, predicting gender is not particularly useful because that's, you don't want to have to take a picture of someone's eye to tell their gender. But it turns out there's a bunch of other things you can predict from these retinal images that are all sort of related to your cardiovascular health. You think about age, that's heavily related to your cardiovascular health. Things like hemoglobin levels, things like that. You can actually make a pretty good prediction of someone's cardiovascular health from a retinal image. And in fact, we have now a new biomarker, a new kind of test that is not invasive. You essentially take a retinal image rather than a blood test, which is traditionally how you would get this kind of level of accuracy. So that's kind of cool. Like, we've discovered something new from retinal images via machine learning. The other area that's kind of exciting is predictive tasks for sort of more abstract things in healthcare. So given a patient's medical records, can we actually predict the future for that patient? That's essentially what doctors are trying to do. And deep learning methods for sequential prediction are becoming quite good. Our group has been working on sequence-to-sequence models for quite some time, which are useful for a variety of different tasks, including translation. And if you look at the results we've been getting in translation, they're pretty significant increases over the accuracy of the old systems, which did not use deep learning, almost to the point of achieving bilingual human quality in a variety of language pairs. But it turns out that these same techniques can be used for medical records. So if you view a medical record as a sequence of events in time, and you take a prefix of the medical record and you try to predict the future of it, then that turns out to be useful for answering a bunch of questions that doctors and healthcare workers want to answer about patients. Will this patient be readmitted to the hospital if I release them now? How long are they likely to stay? What are the most likely diagnoses for this patient right now? And so we've been collaborating with several healthcare organizations using de-identified medical records to see how well we could predict some of these kinds of tasks. And in January, we released a paper that talked about how well we can do some of these tasks and the general approaches we were using. And I'll show you just one result there on the graph on the right, which is predicting risk of mortality for patients. And what you can see is that the baseline method as a dotted line at the bottom there is quite a bit lower in accuracy than the techniques we're able to use, which essentially use every bit of information in the medical record. The baseline techniques tend to use a few handcrafted features to make these kinds of predictions. And the accuracy is actually such that 24 hours earlier, you get the same level of accuracy. So that really gives you a sense as a physician, this is a patient I should really be paying attention to, and you get that warning a day earlier. And that really allows you to focus attention where it should be focused on the patients that are most at risk. So many of those grand challenges actually relate to understanding chemistry and material science and things like that. We've been doing a little bit of work in the field of quantum chemistry problems, and I think that this is indicative of machine learning kinds of work that might be useful for all four of these of the challenges. So one of the things that quantum chemists want to do is they want to be able to take a molecule configuration and then predict various properties of it. Is it toxic? Does it bind with a given protein? What are its quantum properties? And so on. And the traditional way that you do this is you have a fairly computationally expensive simulator called a density functional theory simulator, sort of a traditional high-performance computing-based code. And you run it, and an hour later, you get the answer for a particular molecule configuration. So it turns out you can use that simulator as a trainer for a neural net. And so if you do that, you then have inputs and outputs. Machine learning is very good at learning very, very complicated functions. And it turns out you can learn using a particularly new kind of neural net structure that's particularly suited for these kinds of chemical configurations called a message passing neural net. You can learn a neural net, a model that can actually take in those configurations and produce the same output as the simulator, but can do so much, much faster. In fact, it's 300,000 times faster than the high-performance computing-based simulation. And you can't really tell the difference in terms of accuracy. So that's really just a fundamentally different kind of tool for a chemist. If your tool is 300,000 times faster, you're going to use it very differently. You might screen 100 million or a billion molecules and then find 1,000 of them that are of much more interest and be able to then dive into details for those 1,000. It's just a much different kind of regime. And one of the things we've been trying in general is to speed up the iteration process for various kinds of things. Chemistry here, machine learning research is another thing where we think improving the iteration time for people to try out different experiments just makes people able to come up with new and faster, new innovations faster. Reverse engineer the brain was another one of the grand challenges, and it turns out machine learning is useful for that. So if you take the field of connectomics, which is essentially just trying to understand the static connectivity map of all the neurons in a brain, be it a small animal or a large organism, the way you do that is you unfortunately have a deceased candidate, and then you take their neural tissue and you slice it very thinly, and then you scan each of those slices with an electron microscope. So that gives you something like the second figure here. And then your goal is to take that sequence of slices and be able to reconstruct the connectivity of all the neurons in that volume of tissue. And you can view it as like this kind of jumbled mess where you actually know the connectivity, or if you're a computer scientist, you might prefer a connectivity matrix for how those different neurons in that tissue actually connect. And so it turns out that being able to do this without error is pretty hard because you don't actually know which neuron in this scanned image lines up with the one above it or below it. And so you actually have to kind of trace these images through this 3D stack of slices which has been separated. And one way of measuring progress and how well we're able to do this is to look at the expected run length of neural tissue. How much neural tissue can we trace out before we make an error? And if you look at this graph, the group at Google that's been working on this has been making tremendous progress. It's important to note the y-axis here is a log scale. So they've been able to reduce or increase the run length before they make an error by a factor of about 1,000 in the last 18 months. And that really means we're now able to get to fairly significant sized volumes of neural tissue, things like almost an entire songbird brain or close to a mouse cortex. And that allows us to really do a much better job. And one of the things that led to a big advance here was a technique that they developed called flood filling networks. And so a flood filling network sort of takes a raw image and then a sequence of predictions you've already made about that image, and then uses the entirety of the raw image plus the sequence of predictions you've already made to then predict what is the next most likely thing I should sort of fill in or sketch out. And so you can see it kind of go along the walls of one of these cells here, tracing out regions of high confidence. And then when that confidence dips away, it then jumps off to some other part of the cell where it's now more confident and continues the process. And that's it showing it in 2D. If you look at it in 3D, where you have these 3D stacks of scanned images, you can see it kind of trace along one branch for a while and then kind of give up on that branch for a while and then go back and trace a different branch. And it looks kind of cool. And at the end, you actually get these really beautiful reconstructions of what a neuron and all of its axons and dendrites look like, and all the connectivity to adjacent axons and dendrites. And so they're close to being able to reconstruct the wiring diagram of an entire songbird brain. And the static connectivity is then sort of a really useful property for understanding the dynamic properties of how actual brains work. One of the sort of broadest areas of the grand challenges was engineering the tools of scientific discovery. And really, because machine learning is going to be at the core of many of these different, solving many of these challenges, really engineering the tools means we need good machine learning tools. And one of the things our group has been working on is open sourcing our own machine learning systems that we've been building for doing high volume, high quality training of machine learning models and inference. And so we released TensorFlow as an open source project about 2.5 years ago. It's got a very flexible Apache 2.0 license, which means people can take it and do sort of whatever they want with it. And we now have a pretty active and vibrant community of people using TensorFlow, contributing to improving TensorFlow, making it run on lots of different hardware platforms, making it run on different operating systems, and then people building on top of that and using TensorFlow to open source particular models for training machine learning systems using TensorFlow code as the way they express those kinds of computations. And so you can see here a graph of GitHub interest that different people have to different open source repositories for machine learning. And you can see TensorFlow has really taken off and has really got this nice, vibrant community that is working collectively to improve it. And here's just a few examples of things people outside Google have done with TensorFlow. So there's a company in the Netherlands called Connectera that essentially builds fitness sensors for cows. And it's kind of a cool thing. They can tell if one of your cows in your dairy herd is limping a little bit and that it needs medical attention, or is it unhealthy in some way, from these Fitbit-y things for cows. Other people are using TensorFlow models to detect chainsaw sounds from very far away, to detect illegal logging in areas where that's a big problem. There's a group at Penn State and the International Institute of Tropical Agriculture's office in Tanzania that is using deep learning for doing image-based detection of cassava disease. So cassava plants are one of the most important sources of nutrients. They're the third most popular source of carbohydrates in the world. And many people rely on them for their basic nutrition. And they now have a model where you can, as a cassava farmer, you can take a mobile phone out and take a picture of a leaf, and it will tell you that plant is healthy, or if it's diseased, what disease it is, and what you should do to sort of treat that disease. So it's healthcare for plants, I guess. And these are great examples of things that I think are pretty interesting uses across a really wide spectrum of different areas. One thing that I think is important, though, is the ability to bring machine learning to many more problems. And so if you think about how machine learning problems are solved today, we essentially have data for some problem we care about. We have computation in GPU cards or TPUs or whatever compute devices we have. And then we have someone with machine learning expertise sit down and figure out how to put it all together, what kinds of models to train, what learning rate to use, what kind of model structure to use, what is appropriate for this problem. And they stir it all together and do a bunch of experiments, and eventually they get a solution for the problem. And that's great, but it really limits the scope of machine learning and its impact in the world. Really, there are tens of thousands of organizations that are solving machine learning problems this way. And there's probably tens of millions of organizations that actually have data that could be used to solve machine learning problems and have real problems that machine learning could benefit, but don't have the in-house expertise to solve this. So can we make the approach to solving these kinds of problems much more of the form of data and then use more computation to replace the need for so much machine learning expertise? And I'll walk you through an example of this. So one particular piece of work in this area we've been doing is a technique called neural architecture search. So when a machine learning expert sits down and tackles a problem, they make a bunch of decisions about what kind of model structure they're going to use. How many layers, what size layers should those be, how should they be connected to each other. And the idea here is we can actually automate this process via a model generating model. So we're going to train the model generating model to generate good machine learning models. And we're going to then use the trained objective function on the problem we care about as a reward signal for this model generating model to steer it towards model architectures that seem to work well and away from ones that seem to not work well. And so the way this works, the controller proposes these machine learning models. We train and evaluate them, which is pretty computationally intensive, but it gives us the reward signal we want. So we know that one of these is 78% accuracy, one of them is 97%, and so on. And you just iterate. And it comes up with these kind of funky looking architectures that don't really resemble the kind of more structured things that human machine learning experts come up with, but they're actually quite accurate. So if you look at this graph, this shows you for the ImageNet problem, where you have essentially a color image and you want to detect what is in that image, a bunch of different kinds of machine learning models generated by human machine learning experts. And the x-axis is the computational cost of those models. So generally, as you apply more computation to these problems, you get higher accuracy. And so the y-axis is accuracy. And you see this kind of frontier of trade-offs of the best model versus computational cost trade-offs that you can get. And each one of these black dots here is essentially years of effort by the top machine learning researchers and computer vision experts in the world. So each one of them sort of advanced the state of the art at the time it was released. And if you look at AutoML, it's actually significantly better than all of these experts' output. And it's true both at the high end, where you care about the utmost accuracy and don't care that much about cost. You can get a little bit more accuracy with significantly less cost. And at the low end, you can get much more accuracy with the same computational cost. And the low end is where you might want a model that runs effectively on a phone for detecting cassava diseases or something like that. So that's pretty exciting, right? Basically, we can use computation to get better than human expert level accuracy for these problems. And this has actually been released as a Google Cloud product for vision problems. We're working on extending it to other domains as products, but it's pretty exciting that people can now solve an automated a vision problem that they have without any real machine learning expertise. You just have to be able to get photos, get images, and label them with the classes you care about. Be it broken or not broken parts on your assembly line, or cassava plants, whatever it is that you care about. So deep learning is also transforming how we think about designing computers. And partly because that's when we need more computational power to train these larger, more accurate models, and also to do things like AutoML. And if you look at all the deep learning models that are sort of prevalent today, they have two really important properties. So one is that reduced precision is OK. These models and computations are fine with one significant digit of precision. They don't need the much higher levels of precision that most computational devices today provide. And the other thing is that a handful of specific kinds of operations, mostly in the family of linear algebra operations, things like matrix multiplies, vector dot products, things like that, make up the entirety of the computation of these models. So that leads us to be able to build customized hardware for these kinds of problems that is much faster and much more targeted at running these kinds of computations extremely efficiently and quickly. And so this is our tensor processing unit, the second version of it. And this is a device that supports both neural net training and inference. And if we zoom in to one of the chips on this device, you can see that it's essentially a really large matrix multiply unit, plus some scalar and vector units, plus really high-speed memory. And that is a very simple architecture that happens to run these kinds of models extremely well. And then if you look at the entire device, it's 180 teraflops of compute. It's got 64 gigabytes of HBM memory. And it's not just that this device is fast, but it's also designed to be connected together into much larger configurations. So this is what we call a TPU pod. And these pods are 64 of these devices, which is about 11.5 petaflops of computation. Reduced precision computation, admittedly. But as a basis of comparison, the number 10 supercomputer in the world has about 10.5 petaflops of compute in higher precision arithmetic. These pods are quite powerful, and as I'll show you. The important thing about this as well is that these are programmed via TensorFlow. So you can take the same TensorFlow program, and with only minor modifications, it'll run on CPUs, it'll run on GPUs, and it'll run on these new TPUs. And the same program scales via synchronous data parallelism because the interconnect is very fast on these devices without modification on everything from the single device all the way up to the pods. And these are now available in Google Cloud. As TPU devices, you can get a virtual machine with one of these devices attached and then run TensorFlow programs on it quite quickly. People seem pretty happy with it. You know, what normally could take days now takes hours. That's kind of the iteration speed thing that we want to make available, and that's just using a single one of these devices. You know, moving TensorFlow workloads to TPUs has boosted our productivity, both because it's simpler and it reduces the time required. And they run a whole bunch of models. One of the things we've been doing is putting together reference models for a variety of different kinds of problems that people care about and open sourcing them. So on GitHub, you can find all these different models. And there's more of them coming. And we regularly test these every night to make sure they converge to the right accuracy as we expect them to. So you can sort of depend on these as good building blocks for your own machine learning work. Some success stories of these TPUs. So we have an internal search ranking machine learning model, training that on a quarter pod. So 16 of these devices can be done in about 9 hours versus 132 hours that it used to take on a 200, almost 300 CPU machines. In a large image model internally gets about a 10x speed up in how fast it converges. The WaveNet production model inference for converting text to speech when you talk to your Google Assistant is running on TPUs and generates speech at 20x real time on one of these devices. And we've been working on improving the software stack. So in December, I gave a talk where I showed these results where we could train a ResNet model, a particular kind of ImageNet model, to 76% accuracy. Took us 1,402 minutes on a single device, 45 minutes on a half pod, 22 minutes to get to almost that level of accuracy on a full pod. And then we've been able to make significant software improvements. So this is the same hardware, but it's 45% faster through software improvements as our software stack has been maturing. And if you look at that, in 12 minutes, we can converge an ImageNet model on a pod using 64 of these devices, which is an ImageNet training epoch every 8 seconds, 1.2 million images. So that's really just a fundamentally different kind of scale and turnaround time for these kinds of experiments. You can try many more ideas out, really get a good sense of what things will work, what things will not in 10, 12 minutes instead of overnight. And this was the scaling graph we had in December. It looks better now. And this is, there's a Stanford University project has started to produce a set of machine learning benchmarks called DunBench. And one of them is ImageNet classification on ImageNet, image classification on ImageNet. And one of them compares the cost of running these things on various cloud solutions. And you can see that the cost for training on a TPU to 93% top 5 accuracy is roughly $82 on one of these TPU devices, which is about 4x better than the second best result, which is obviously good. You can try 4 times as many experiments for the same price and do them faster. OK, so I want to touch briefly on machine learning for systems, because I think that's kind of an interesting, we've been doing a lot of work on building systems for machine learning. But now can we turn that on its head and talk about what we can do in terms of machine learning for computer systems? So today, lots and lots of computer systems, low-level things like operating systems or compilers or storage systems, don't really make use of machine learning. And instead, they have lots and lots of handwritten heuristics of things like, should I compile this particular bit of code this way or that way? And they have some hand-coded decision about that. Or should I insert this block into the storage cache, block cache? And really, I'll give you one example. So in traditional database systems, in order to find things in a sorted order on disk, you use something called a B-tree. And a B-tree allows you to essentially take a key and then predict which particular block on disk must have that key if it exists at all. So you essentially can view this as a model, right? It's taking a key and making a prediction of where on disk it must exist if it does exist at all. So we can actually replace a B-tree, which essentially is a multi-way branching tree that just sort of methodically compares the sequence of characters in the key at each point in the tree until you get down to the leaves. You can replace that with a neural net and actually take in the key and have a neural net just look at the characters in the key and make a prediction of where in the data that key must exist, if it exists at all. And so this actually turns out to be pretty effective. And if you look at the sort of a way of thinking about this problem, you're essentially trying to predict the position of the key in the cumulative distribution function of the key space. And by having knowledge of the distribution of actual key values, rather than trying to abstractly model all possible distributions, you can take advantage of patterns in the key space. So for example, if you have stuff that is, you're trying to sort log entries by time, maybe you have fewer log entries on Saturdays and Sundays than you do during the weekdays. And the neural net can actually take advantage of that by incorporating that into the predictions it's making about where in the key space something must exist. And you can see in this data from this paper, it actually performs quite well even on CPUs. So if you look at a B-tree, and you look two rows down, you can actually get something that is 60% faster than a B-tree using this approach. But perhaps more importantly, it's 1/20th the size. Or you can make different trade-offs and get something that's a bit faster than a B-tree and 1/100th the size. And this is really quite different than the B-tree approach. And this approach also works for hash tables. So you can replace a traditional hash function, which must work for arbitrary keys, with something that can take advantage of the properties of the key space and actually give you something that sort of makes better use of the buckets in a hash table, leaves less empty space, and therefore has significant space improvements. Bloom filters are another thing that allow you to predict which elements are in a set. And they have to work on arbitrary sets of keys. If you have knowledge of the key space, you can actually train a neural net to do this and get sort of a 36% space improvement over Bloom filters with the same false positive rate. So these are sort of pretty transformative things if you start looking in the core of computer systems problems, how you might apply machine learning to them. So where else could we do this? Lots of places, right? Because these computer systems are filled with these kinds of heuristics or traditional data structures, compilers, networking code. All these heuristics that are written have to work well in the general case. They can't really take advantage of the actual pattern of usage very much. And by learning, we can take advantage of that pattern. And so anywhere we're using these heuristics to make a decision, I've listed dozens of different places we might think about doing this. And I think that's pretty exciting. Many programs have kind of user configurable performance options. And really, those are just a pain for users of your program. Like, how many event manager threads should I have? 16 seems to work on whatever hardware I'm running on today. But if I run on a slightly different machine, I might want 24 or 32 or 8. And really, those kinds of things should be automatically learned. Getting back to the AutoML idea, we can actually meta-learn many, many things about machine learning problems. We can learn how to place computations. We could learn fast kernel implementations for things like convolutions or matrix multiplies. We could learn optimization update rules. Our group has some papers on that. Learn input preprocessing steps. How should we crop and warp images to improve accuracy of models? I think there's tons and tons of opportunity here. So the key for success in these kinds of settings is you really need a numeric metric to measure and optimize. That's where these reinforcement learning-based approaches work best. And you need a clean interface so that you can easily sort of take existing operating system code or compiler code and have a learned decision be sort of in the middle of that rather than a hand-coded heuristic. We're working on how we can develop APIs that will make this easier and not too intrusive in existing code. So in conclusion, I have a couple of things to say. One is I think the field of machine learning hardware is really at its infancy, and faster systems and wider deployment is going to really lead to more breakthroughs because people will be able to try out ideas more quickly. We'll be able to automate much more of the machine learning process, apply it to many more problems. It's going to be really exciting. And learning in the core of computer systems, I think, will also make them better and more adaptive. And we're just starting to kind of touch the possibilities there. So with that, thank you. There's more info on those different URLs. And I'll take questions, I guess, from Twitter. Thank you.